I've had this Rode VideoMic Go for a while now. It works better than the camera's built-in mics for sure, but I've seen some performance issues that don't quite add up. The official specs claim it can handle up to 120 decibels, which is pretty dang loud, uncomfortably so even. For reference, I'm recording small indie idol shows, not bone-shaking rock concerts, yet there's the unmistakable crackle of clipping in the tracks when I listen to them afterwards. When I plug the mic directly into the camera, I can see the on-screen VU meters are not peaking. It's as if the audio is clipped before it even gets to the camera. Meanwhile, if I plug into my wireless Go 2 kit, it seems to give me a little bit more headroom, but the input stage is more sensitive, so that clips instead, which doesn't solve my problem. So what's going on here? Time to do my thing and find out! The Rode mic is an electret microphone. If I pull the sock off, can just see the back of the capsule in here through the vent slot. This type uses a low voltage bias power or plug-in power. This differs from the 48 volt phantom power provided to condenser microphones. The bias voltage powers a tiny JFET built into the capsule itself, which will act as a buffer. What I believe is happening to this mic is it has insufficient voltage, so the JFET will saturate, causing it to clip internally, even if the input stage of the device it's plugged into does not show it clipping. A little bit goofy setup with my secondary camera on the tripod and my main camera on the workbench, but here's my test rig using this Y-splitter to break out and take measurements of the various voltages fed to the microphone. The sleeve is ground, the ring and the tip are supply and signal. Look at that, 1.427 volts. Okay, so that's the power being supplied to the microphone. If I unplug the microphone from the camera, 2.4. That's interesting. Meanwhile, my Rode Wireless Go 2 kit provides a much more reasonable 2.17 volts to the microphone. Taking the mic out of the circuit, and that provides a 3.31 volts open circuit. I could fix the headroom problem by buying a better microphone, or I could buy a pile of parts and try to make a preamp that'll solve the problem for me. Here's my proposed solution using an op-amp as a unity gain buffer. Potentiometer P1 and fixed resistor R1 will allow a tunable bias voltage to be applied to the microphone. Capacitor C1 will block this DC voltage while allowing the AC signal from the mic to pass through. R4 and R5 are matched 10K resistors, which will bias the input at exactly half of the supply voltage. The circuit is operating off a single-ended supply from a 9-volt battery, so the biasing is important to make sure that the output stays in its linear range. The output of the op-amp will feed directly back to the inverting input for unity gain. R3 is a little 10 ohm resistor to reduce chance of oscillation when driving capacitive loads. C2 will block the DC component while allowing the AC to pass through. R2 is a 10K ohm resistor which will prevent any buildup of charge on the backside of C2. I'm using an NJM3404AD low-power, single-ended supply, dual op-amp package. The goal is to have the packaging largely constrained by the size of the 9-volt battery that will be powering it. This width will conveniently hold three 3.5mm tip ring sleeve connectors. Why are there 3 and not 2? Wait and see, you'll find out. Quick sanity check of the board layout. This is a prototype, it's 1 of 1, I'm figuring this out as I go. Power supply capacitor, audio input and output capacitors, microphone bias voltage tuning potentiometer, and the support resistors for those. Op-amp is going to live right about here. I am leaving extra space because this is a dual op-amp and I may need that second channel for additional amplification. I've made this mistake before, so I'm double checking that the potentiometer's resistance will reduce at the wiper as I turn it clockwise. This will mean turning clockwise will increase the bias voltage to the microphone. Got the bulk of components and jumper wires in place. Now I better start soldering some of it down so it doesn't run away. Backside of the board is pretty dense now. Have to be careful I don't bridge anything that shouldn't be connected. If you're enjoying my antics, drop a like to help more people find this video, and consider subscribing if you haven't yet. More info, links to my socials, and ways to support the channel can be found in the description below. Got the circuit board wired up, ready for testing. Used another pair of 10K resistors to tie the non-inverting input of the second op-amp in the package to one half of the supply rail. The output and the inverting input are tied together with these wires and the wire nut just so that it stays in a known state, doesn't do anything dumb. Using a 9-volt battery for supply, just as the final circuit will use. Got a 470 ohm resistor as a current limiter in case I've really made a mistake. This meter is input current. Middle meter is input voltage. Left-hand meter is going to be the roamer. Right now it's tied to the non-inverting input of the second package. I'll move this around just to be sure the rest of the circuit is working. Moment of truth. Please don't blow up. So far so good. 2.2 milliamps, that's about what I expected given this combination of components and quiescent current. Only about 1 volt dropping across the limiting resistor, and the mid supply is 1/2, exactly. Everything is as it should be. Touching the left meter to the bias power for the microphone, this has no load on it, so it's going to float at exactly the supply voltage until it is loaded down with something. Tilting the board to give access to the bottom lets me measure the voltage at the non-inverting input of the first op amp in the package. That is also sitting at exactly 1/2 of the input voltage. The output is floating likewise at exactly 1/2 of the input voltage. Measuring at the signal output, we have effectively 0 volts DC, just as designed. Left meter now hooked to the bias power supply for the microphone. This 10K resistor is going to pretend to be the microphone in terms of electrical load. Going to connect that to ground. Current rises slightly. Input sags because protector resistor is still in circuit. Bias power drops from equal to the input to a more reasonable 5.67, 5.68. Making a fool out of me. Removing the limiting resistor from the circuit gives it the full 9.39. Bias voltage rises, obviously. If I take this tiny screwdriver and adjust the bias potentiometer, I should be able to adjust that up or down. Let's make sure I can actually turn that down pretty low. This is a multi-turn potentiometer. 5, about the lowest I can go. 5K pot, 3.3K resistor. I may need to increase the resistor. These were just chosen based on typical values for a bias resistor. Putting a big 470 ohm resistor, increase the input current a bit, drop the bias voltage down to under 1/2 volt. 3.3K resistor gives us 2.64. Got the microphone here, plugged into a tip ring sleeve jack. If I wasn't nervous before, I certainly am now. Green is ground on the large tab. The tip and ring should be the same connection internally at the microphone. I do have another limiting resistor just in case. It drops to 4.4. Slight increase in current. Since I'm pretty sure it's not going to go up towards 200 milliamps, going to change the scale. Gives us a little bit more resolution. 600 microamps. Change the position of the meter so it's now going to read the actual bias voltage applied to the microphone. Interesting, that's putting a full 4 volts to the microphone, so this one is even less power hungry than I thought it would be. I'm going to need to make some changes. Input current, input voltage, bias voltage. I added a single wire from the other end of the bias potentiometer to ground. It can now provide the full range of voltage. If I turn it up, that increases. Can turn it down. Gonna start right around there at 2.5. Plug in the microphone. 1.27, 1.28, somewhere in there. Reasonable, but 1/2 of what the microphone calls for. It's around the voltage the camera would provide to it, and that's what would cause the clipping. Reconfiguring the meter lead, so I'm not using the safety resistor anymore. Now I have the bias connected directly to the microphone. Quiescent current for the circuit is 4.16. Connecting the microphone has added just about 100 microamps. Now I'm going to carefully raise the bias voltage until the microphone is seeing about 2.5. There's 2.6. Gonna call that close enough, 2.501. Current has increased a little bit, 4.17 quiescent, 4.34 with the microphone in circuit, 4.26 for the bias without the microphone in circuit. That's plenty safe, it's not gonna hurt anything connecting that. Next question will be, can I raise the bias further without the current going through the roof? Microphone specs talk about 2.5 volts and 330 microamps. Right now we are just shy of 200 microamps. I should be able to give it a little bit more bias. How about a hair over 3 volts? So there's the specified current for the microphone, using a whole ½ volt higher than the spec calls for. That's interesting how it creeps up a little bit after it first stabilizes. In light of that, I'm going to back that down a little bit. There's closer to 3. Probably about time to get the inputs and outputs hooked up on this thing so I can see if there's signal passing through. Temporary wiring situation, so it is quite messy on the workbench, but we are so back. Have the Rode shotgun mic? No, it's not the time. The microphone is hooked up to my buffer amp. Output of the buffer goes to the transmitter of the Wireless Go 2 kit. Here's the receiver, you see the VU meter moving, and in fact you're hearing me speak through this circuit right this second. I'd say that's working. In this test here, I have the microphone hooked directly to the camera as it will be in the intended application. Got my sound level meter here, about the same distance from me as the microphone is. I can still easily appear to peak it out, at least according to the meter on the camera. Ah! Yeah, that looked like it peaked. Now I've hooked up two 10k ohm resistors as an attenuator. Should cut the signal by half. Ah! There's over 110. From looking at the waveforms, this thing might be okay with unity gain, but I might want the option of dropping the gain. I could do a fixed attenuator, I could do a direct potentiometer, or I could use that second stage as another buffer. First op-amp on the package buffers the microphone, can then have the attenuator, then the second op-amp on the package buffers the output. This will allow the output to have plenty of current drive, but I can choose how much to attenuate the signal, whether with a potentiometer or a set of dip switches. I'm liking that idea. Here's a plan for the attenuator and the output buffer. Have a 4-position dip switch, and can use a combination of resistors to get a range of attenuation values, with a 47K, 23.3K, a 10K, and a 6.6K, some of which are by combinations. I should be able to get 0, 3, 6, 9, or 12 decibels of attenuation. This should cover all the range I need, considering that the system as is about where I want it to be at 6. If I really need to knock it down, I can go further. If I want a little bit hotter output, I can always reduce it. I will need to use capacitors to block the DC component of the signal. This will make sure that only AC signals are amplified, and only AC signal is output. Dip switch and attenuator resistors are wired up. I'm not winning any points for elegance, but it will work. Just spent far too long troubleshooting why I had no output signal, only to find this solder joint right here didn't take. This is the interstage connection between the attenuator and the second op-amp. No connection, no signal. I feel dumb now. Sometimes it really can be the simplest things that will trip you up. Now I should have signal on the output. Hooked up to the camera, both stages are working. So far so good. Did some calculations to find what combination of dip switches would give a certain amount of attenuation. The ones with arrows are ones that are most interesting to me, namely 0 dB straight through, 3.1, 6, 8.7, and 11.9. There's some intermediate ones. I could do 8, 8.4, 9.4, as much as 12.4, as little as 1.7. We'll put a tone generator up near the mic, and then I'll flip the switches and make sure that they do the right thing. Okay, got the mic over here, tone generator pointed at it. Another shout test before it's too late. Looks like the attenuator is working as designed. Time to clean up the circuit board. Remove the long signal pigtails, putting in little 2-pin headers. The jacks will have the pigtails with little 2-pin connectors. This will allow the jack side to be removed, and it means I can continue the assembly and testing without having the enclosure built yet. Been a while since I used these connectors. Let's hope I'm not too rusty at it. One crimp on the jacket, one crimp on the conductor. That one worked. Arrow side is going to be signal. Why is that not taking? Definitely a problem, these aren't latching in. In order to get the inserts to latch, I needed to trim just a tiny bit off the catches on these connectors. Annoying, but it is what it is, I'll make it work. Giving it a twist, more for mechanical stability than any sort of noise rejection. Plus, I think it looks cool. Probably need to adjust how they're coiled or folded up when it's put together, but that's getting closer. Can probably solder 2 of the jacks on and get moving there. Heck. Cleaning up the board, finalizing its footprint. We'll use the utility knife to score the board and then break off the excess. I like to brace the board over the edge so I'm not putting as much force on the solder joints. I use the existing perforations as a guide. That should be enough. Big emphasis on the should. Using the corner of the table. Once started, the crack should follow. There you go. Not the prettiest, but it'll work. For small sections like this, I'll just use the needle nose or another pair of pliers. As the final component mounted on the board, a very discreet little red indicator LED to show the power's on. From the looks of things, it's added maybe 2/3 of a milliamp to the total draw. Not such a big deal. Just bright enough that I'll be able to see it when I look in through a hole in the side of the case. Time to start putting it together. Whipped up a 3D printed enclosure with a lid, holes for the input and output jacks, hole for the little power on LED. The lid has a compartment to hold the battery, and a slot for the power switch. I used some parts from my cold shoe accessories kit for the mounting solution. It's got the shoe and its lock nut. It's a 1/4-20 stud, so I have a little nut and a fiber washer on this side, lock nut and another fiber washer on the inside. The recess keeps the stud and nut away from the circuit board. The ribs lend mechanical strength because the 9-volt battery makes this unit a little bit heavy. Next step, lay down a little bit of foam just to keep the circuit board up off of the ribs and keep it nice and balanced. Little bit of electrical tape just to keep everything from jumping around. Should be able to slide the circuit board in now. Measured it to be a little bit of a snug fit. That's exactly what I want, so it wants to stay in place. Slide it all the way this way for some clearance reasons. Got the jacks mounted. Going to do a final test before finalizing some connections that'll make it a little bit tougher to disassemble later. Mic check. Mic check, mic check. I mentioned there'd be something about the 3 jacks that you'd find out later. In this final configuration, top jack will be from the shotgun mic. This bottom jack will be output to the camera. This middle jack is a passive pass-through to the other channel of the output to the camera. I can now connect 2 independent sources, one of which may be remotely mounted. Let's give it a try. Battery is not hooked up, circuit is not powered. You're hearing me pass to the wireless Go, through the pass-through, and up to the camera. Now that I got some power on the circuit, should be able to hear me from the wireless Go here on the left side, or from the shotgun microphone here on the right side. Got the switch clipped into place. Wiring's a little bit messy, but you know what they say, there is nothing more permanent than a temporary solution that works. This is prototype 1 of 1, so I'm not too bothered. Battery snaps in there, hooks here, presses down, mostly stays in place. It's a little bit rattly, unlikely to simply fall out. And of course I can now power it on and off with the switch. Fitment of the lid is very tight. That's by design, so that it's not likely to just pop off by itself. I really did not have time to design in some fancy clips, latches, or anything like that. Okay, maybe I made the lid a little bit too tight. And call that a good amount of tight. This thing looks ready to rock and roll. Mic check for the lav mic. Mic check for the shotgun mic. Yeah, that's working. Project was a bit rushed at the end there because the event I needed to use it for was coming up fast, but I call it a resounding success. I was able to get shots from inside the crowd, right up close to the stage, even right next to the PA speakers, and my mic didn't clip. I used the wireless kit to mount a low-sensitivity dynamic mic close to the PA speakers to get a clean audio feed that was consistent regardless of where I was in the venue. Even got to really push its limits at a jam session afterwards with some friends. I'm pretty sure Rode did not spec the VideoMic Go for up close with a drum kit, but it was able to handle it. Just had to click the attenuator down another notch to -9 dB. Certainly opened the door for more audio projects in the future, so keep an eye out. Until next time.